When we're troubleshooting BGP, one of the key things we need to understand is how does BGP make its path selection decision? There are several different questions that BGP can ask as it's making this decision, and that's what we want to review in this video, BGP path selection. This table on screen is a comprehensive list of everything that BGP might consider as it's making its path selection decision, and notice I said this is comprehensive. This is more than you might see in some documentation out there, and the reason is some of this deals with more advanced configurations like having a route reflector or multipath BGP. These are things that we're not concerned with at the CCNP level, but things you would want to acquaint yourself with if you go for the CCIE in routing and switching. But I wanted to give you this comprehensive listing, but focus on what is most important. Things that you're more likely to deal with on a day-to-day basis, as we're trying to influence inbound and outbound BGP path selection. But let's go through this complete, comprehensive listing first, so that we can be exposed to everything. These path selection parameters are listed top to bottom in order of preference, and the very first thing we see listed is weight. This is a Cisco-specific parameter, and it's locally significant to our router. This is not something that gets advertised out as part of an advertisement to a neighboring router. But let's say that we've got a route coming in from a neighbor, we can assign it a particular weight. And routes that we received from a different neighbor, we could give them a different weight. And when we're trying to decide on an outbound path, we could look at those two weights and we could go with the path that has the higher weight. A higher weight is preferred. And another very common parameter to use to influence an outbound path selection is local preference. Again, higher is better with local preference, and unlike a weight, this is not a locally significant value. This local preference information for a route is communicated to all of the routers within a single autonomous system. The next parameter is asking, from where did this network prefix originate? BGP is going to prefer a route that was sourced from a network statement, or maybe a redistribute statement. Those are going to be preferred over routes that are injected using the aggregate-address command. Next is AS path length, or autonomous system path length. This is the number of autonomous systems that we have in the AS path attribute. It tells us which autonomous systems we have to travel into in order to get to our destination network. And here, much like hop count is used by RIP, we prefer a lower hop count. Here, a lower number of autonomous systems is preferred. A lower AS path length is going to be preferred over a longer AS path length. The next parameter is the origin type, which is asking how was this route injected into BGP? Was it injected by an IGP, an interior gateway protocol? Was it injected by an EGP, an exterior gateway protocol, which would be BGP in any modern network? Or do we have incomplete information about that? Well, an origin type of an I is going to be preferred to an origin type of an E, and that's preferred to an unknown origin type. In other words, the question mark, the incomplete information. Next is the MED, the multi-exit discriminator. We commonly use the MED to influence inbound route selection. For example, let's say that we were connected out to the internet via a couple of internet service providers, and maybe the bandwidth to one service provider is greater than the bandwidth to another service provider. What we could do is use the MED to influence which service provider is going to be used by hosts out on the internet as they're coming into our autonomous system, and a lower MED is preferred. The next parameter is paths, and what we're saying here is that we're going to prefer an eBGP path, in other words, a path between different autonomous systems, as opposed to an iBGP path, a path within an autonomous system. And the next parameter is a tiebreaker. If everything is a tie up to this point, we can say that we're going to look at the IGP metric that gets us to the next hop IP address, and we're going to go with the lowest IGP metric. For example, if we're running OSPF as our interior gateway protocol, our IGP, maybe we've got different OSPF metrics to get to different next hop IP addresses. We can go with the path that has the lowest metric to get to the next hop IP address. Next, we're asking a question. We're asking whether or not BGP multipath is enabled. Do we need to have multiple paths injected into our routing table? And if we do, but we've not yet selected a best path, then the interrogation of these parameters continues, and the next parameter is age. Here we're asking which eBGP route is the oldest, and the oldest route is preferred. The next tiebreaker is the router ID. We're going to prefer to use a route that we learned from a router that had the lowest router ID. And the next parameter, minimum cluster list length, that's not something we're really concerned with at the CCNP level. It deals with a route reflector BGP configuration. But if we do have that kind of configuration, we're going to prefer the route that has the minimum cluster list length. Again, not something we need to worry about for the T-Shoot course, but I at least want you to be exposed to it. And the final tiebreaker is asking which of my neighbors has the lowest IP address, and I'm going to prefer the neighbor that has the lowest IP address. And if you count up all of these different parameters in this table, you're going to see that we've got 13 parameters. That's a lot. That's a lot to remember. And I've heard different memory aids to help you remember the BGP path selection parameters. And I want to share with you here in this T-Shoot video the simplest memory aid that I've come across. It does a great job of helping us remember some of the key components in a BGP path selection decision. It's not totally comprehensive. It doesn't, for example, get into route reflector considerations, but it is useful the vast majority of the time. And by the way, this is not a memory aid that I came up with. This is just one of the more popular memory aids that are out there. It's actually an acrostic, and it goes like this. We love oranges, as oranges mean pure refreshment. Let's translate what that means. The W in wait is reminding us of the W in we. We helps us remember wait. We love, the L in love reminds us of the L in local preference. We love oranges, well, the O in oranges represents the O in originate. We love oranges as, the as reminds us of the AS in AS path length. We love oranges as oranges. This O is reminding us of the O in origin type. Remember, origin type says how was the route injected into BGP? I is preferred to E, and E is preferred to question mark. We love oranges as oranges mean, and the M in mean reminds us of the M in the med, the multi-exit discriminator. The lower the med, the better. We love oranges as oranges mean pure, the P in pure reminding us of the P in paths. We prefer E BGP paths as opposed to I BGP paths. We love oranges as oranges mean pure refreshment. The R in refreshment reminding us of the R in router ID. This table might be a bit easier to memorize. And again, it's helping us remember the acrostic, we love oranges, as oranges mean pure refreshment. But I'll admit, this is still quite a few things to remember. What do we, from a practical standpoint, need to do as network engineers to influence outbound and inbound path selection? Well, since we're probably not going to be able to configure the service provider's router, I'll look at just 4 parameters that we can modify on our routers to help us influence that inbound and outbound path selection. Specifically, we can configure the wait, the local preference, the autonomous system path length, and the med. Those are the primary 4 BGP path attributes that I think of from a real-world perspective when I'm trying to troubleshoot path selection or to influence path selection.